everyone, my name is Adriana Martinez and I am a junior mechanical engineering major. I did my research with Dr. Keshav Shrestha over the evolution of magnetic properties of europium-doped calcium iron arsenide, which is a superconductor. Now, what is a superconductor? A superconductor is a unique material that experiences zero electrical resistance below a certain temperature, also known as the critical temperature, meaning that this material can conduct electricity without loss and will also expel all external magnetic fields. There are multiple types of superconductors that have been found since their original discovery in 1911, such as copper-based, iron-based, and heavy fermion superconductors. The superconductor that we focused on is an iron-based superconductor, more specifically, europium-doped calcium iron arsenide, where the doping amount is at various levels from 0 to 1. This superconductor is a part of the type 122 superconductor family. In this family of superconductors, the magnetic moments of the material appear as a spin density wave at temperatures ranging from 170 Kelvin to 190 Kelvin. In addition to their spin density wave, this type of superconductor also experiences a strange magnetic anomaly in the lower temperature range for the higher dope samples. This research in particular focuses primarily on the change of magnetic properties that calcium iron arsenide experiences upon europium doping. The single crystals of the europium-doped calcium iron arsenide were grown and obtained from an outside lab. The magnetic susceptibility data is then gathered and analyzed using the Curie-Weiss model. According to this law, the temperature dependence of magnetic susceptibility is given by the equation chi is equal to C divided by T minus theta, where chi is magnetic susceptibility, T is the temperature of the sample, C is the Curie-Weiss constant, and theta is the Weiss temperature. For the results of the experiment, here we first have the magnetic susceptibility data of the different doping levels graphed as a function of time. Magnetic susceptibility increases gradually as temperature decreases. In the higher dope samples from 15 to 19 Kelvin, there is an anomaly which is shown as a shallow dip in the graph. This dip in the magnetic susceptibility graph arises due to the europium antiferromagnetic spin ordering. The data for europium iron arsenide is also shown as an inset graph here in order to better highlight the Néel temperature indicated by the arrow, in which the anomaly occurs. The red curve on the inset graph also shows the best fit using the Curie-Weiss law. The inverse magnetic susceptibility for the following dope samples are then shown as a function of temperature. The inverse magnetic susceptibility increases linearly with temperature, which follows the Curie-Weiss law. The best fit parameters, such as the Curie constant and the Weiss temperature, are then extracted from these graphs and plotted as a function of temperature. Both parameters increase almost linearly with doping, as shown by the dashed line. In this research, we have extracted the magnetic data properties for europium-doped iron arsenide and have analyzed them using the Curie-Weiss law, which states that the inverse magnetic susceptibility of the sample should vary linearly with temperature. The spin density wave transition was not observed in these samples, meaning that the superconducting state was not induced. However, we were able to view a dip in magnetic susceptibility, which exists due to the antiferromagnetic arrangement of the europium 2+ spins. Even though superconductivity was not reached in these samples, we were still able to see how the magnetic properties of the sample changed with increased doping. We hope to apply this information into finding a sample that can enter the superconducting state at low amounts of induced pressure or even at ambient pressure.